Welcome back to Chapter 3 of Calculus. In this chapter, we're going to be looking at more derivatives. So the derivative study is not over yet, not by a long shot. This chapter will go through a few different new types of derivatives, as well as beginning some more applications. And then the next chapter will get into a lot more applications. In this section, we're going to be looking at the product rule and the quotient rule. Now, these are kind of like the chain rule, where they don't tell us how to take the derivative of a specific thing, but they allow us to take derivatives of more complicated things. The chain rule, we had composite functions, and we used our power rule or trig. And this one will be taking products or quotients of functions that we already know how to take the derivatives of individually. Now we're going to be doing them when they're multiplied or divided. And so if we look at the product rule, um, we can show what this is based off of the definition. If f and g are both differentiable functions, that is important. You have to be able to take the derivatives of each of them individually. When you multiply them together, by the definition, the derivative is going to be, the limit is h goes to 0 of f of x plus h times g of x plus h. We had to plug in x plus h to both of them, minus f of x g of x over h. So that's just the definition. And we can't separate these guys at all because we don't know what kind of function it is. We just have to go with it. But we're gonna do something kind of funky in this next step. We're going to add 0 to the numerator. But the 0 is going to look kind of strange because it's not going to be just a little round thing. The 0 is going to look like f of x times g of x plus h minus f of x times g of x plus h. If you actually do that subtraction, you're subtracting something from itself that is going to equal 0. It just doesn't look like it. So we're going to put that right in the middle. And I did switch the order. I put the -1 first and then the +1 second. But what that allows us to do is we can factor some stuff out. Because this first piece has a g of x plus h, and the second piece has f of x in both of them. So we can factor those guys out. And we have g of x times f of x plus h minus f of x, and then f of x times g of x plus h minus g of x, all over h. I also split the limit up into two pieces here, because we can split it up at that addition. Split it up right there. And so then from here, we can actually split the limit up a little bit more, because this multiplication, we could take that multiplication into its own limit, and this multiplication we can take into its own limit. So when we split that up, we get something that looks like this. And this doesn't particularly look all that great, but we are actually almost done with this derivation. Because when we take the limit, g of x plus h goes to 0, that goes away. That's just going to be g of x. And then this one, limit is h goes to 0 of f of x plus h minus f of x over h. This is the derivative. That's just h prime or f prime of x. Over here, there's no h even in here, so that's just f of x. And this is the derivative of g of x. So that's going to be g prime of x. So when we get that all written out, y prime is going to be g of x times x f prime of x plus f of x times g prime of x. That is the product rule. We have two things multiplied. We're going to take something times the derivative of the other plus the derivative of the first times whatever the second is. Another way of writing it, which we actually use a lot, is if y equals u times v, then y prime equals u dv plus v du. And actually defining what those u's and v's are in each of them is important. It makes big problems a lot less complicated. And it's just a great way of showing that little bit of work. So, and we do like using this one because there's a lot less going on than this one up here where you have the f of x's and g prime of x's and the u's and the v's a lot easier. So let's see how that works. If we have f of x equals x to the fourth sine of 3x, we're going to let u equal x to the fourth and v equal sine of 3x. And now we can take the derivative of each of these separately. Du, x to the fourth becomes 4x cubed, and dv, derivative sine of something is cosine of something, then times the derivative of something. We've got chain rule in here. That's going to be an extra times 3. I'm going to put that on the front. And so we have the two derivatives. Now we're just going to cross multiply, basically. We're going to take these two and multiply, and we're going to take these two and multiply. Then we just need to add them together. And I generally will go with this one first. I like doing that one first. We'll see why in the quotient rule. Here it doesn't actually make a difference, but in the quotient rule it does. So we have that. So f prime of x equals, we have 4x cubed times sine of 3x plus x to the fourth times 3 cosine 3x. It's 3x to the fourth times cosine of 3x. That's it. That's the derivative. That would be product rule. Let's look at another one. f of x equals sine squared of x times the square root of 5x minus 7. So again, define our u's and our v's. Let u equal sine squared x and v equal the square root of 5x minus 7. And so notice in doing this, we're practicing all those derivatives that we've learned so far. Du sine squared of x, that's sine of x squared. So we have something squared, so that's going to be 2 sine of x times cosine of x. This was a sine in there. And then dv, this is something to the 1/2, so we're going to have 1/2 times our something, 5x minus 7, to the negative 1/2, and then times the derivative of that, which is just 5. So that'll be 5/2 times 5x minus 7 to the negative 1/2. Cross multiply. F prime of x. We have 2 sine x cosine x times the square root. 2 sine x cosine x times the square root of 5x minus 7. Plus, we have the sine squared times the 1/2 square root, or the 5/2. So plus, let's go 5/2 sine squared x times 5x minus 7 to the negative 1/2. And there we go. A lot of them, they do get big, they do get ugly, and if it makes you feel any better, I have to grade them all. So even when they're right, they're a pain to look at. But that's what it is. So that's the product rule. Now let's look at the quotient rule. We could prove the quotient rule from the definition, which you're going to be doing in an exercise. We're going to do it here by using the product rule. So we have f and g are differentiable, and y equals f of x over g of x. Here also, g of x can't equal 0. That is important. We can't be dividing by 0 here. Then the quotient rule says, or the product rule, says f of x equals g of x to the negative 1. So we have our u and we have our v. We can find the derivatives. Derivative of f of x is just f prime. The g of x, we have to chain rule. That's going to be negative 1 times g of x to negative 2 times g prime of x. We can multiply them. So we have f of x times g of x to the negative 1, and then times f of x times the whole mess that's dv. We can move to work on simplifying, move the negative exponents down to the bottom. So that one goes to the bottom, that one goes to the bottom. F prime of x over g of x minus f of x times g prime of x over g of x squared. Common denominator is just an extra g of x here on top and bottom. So we have f prime of x g of x minus f of x g prime of x all over g of x squared. That's going to be the derivative. That's the quotient rule. Now again, this is a bit of a mouthful. We have the u's and the v's that we can use. If y equals u over v, y prime is v du minus u dv all over v squared. When I was learning it, we learned a little poem, which I generally don't like those things, but this one still sticks with me, so that means it's got to be at least marginally effective. But it's low d high minus high d low, square the bottom, and away we go. And so that gets it. The two big mistakes in doing this would be getting the top backwards and completely forgetting about the bottom. Sometimes not squaring it, sometimes just, hey, who needs a denominator? Those are the two biggest mistakes in this type of problem. So let's look at a problem like this. We have f of x equals a polynomial over polynomial. I didn't even have trig in this one. You don't have to have trig. We can have polynomials or power. We have square root. We're still going to do the same thing, u and v. We're going to let u equal the top, x cubed plus 5x squared minus 3x plus 2, which means that du equals 3x squared plus 10x minus 3. And v, I think I can get it over here. V is going to be the square root, x squared plus 4x, which means dv, oh, it's not going to work. 1/2 of x squared plus 4x to the negative 1/2 times 2x plus 4. Oh, there we fit it. And then multiplying, this is why I do that one first, because it's v du. That's the first one. Here the order matters. So we do that one first. I do it with product rule just so that I'm in the habit of doing that one first. So f prime of x, it's going to be that times that. So we're going to go 3x squared plus 10x minus 3 times the square root of x squared plus 4x minus, now we go the other direction. Ooh, this one's not going to fit. Make sure you start with plenty of room. X cubed plus 5x squared minus 3x plus 2 times 1/2 x squared plus 4x to the negative 1/2 times 2x plus 4. And yes, you could simplify that a little bit if you really wanted to, but there's times we're not going to. Anyway, this is all over the denominator squared. When you square the square root, you'll just get x squared plus 4x. This is not the prettiest of problems, so I apologize for that. It would take my entire screen here. But again, it's this one times that one minus that one times that one all over the bottom squared. Let's look at another one that's not quite so obnoxious. Let's look at tangent of x. We haven't done tangent yet. We've done sines and cosines. I've also tricked you into doing secant and cosecant, but we didn't call them that. So tangent of x, how would you do tangent of x? Why is tangent of x quotient rule? It's just tangent. Well, but what is tangent? Tangent is sine of x over cosine of x. And so u equals sine of x, v equals cosine x, du, derivative of sine is cosine, dv, the derivative of cosine is negative sine, and then we can put it into the quotient rule. We're going to have cosine times cosine, prime of x equals cosine x, minus sine x times negative sine x, all over cosine squared x. We could simplify this. F prime of x equals cosine squared x, and then multiplying, that'll be a plus sine squared x over cosine squared x. And I know right now the one thing that you are not going to do is you're not going to try and cancel those cosine squareds, because that would be a horrible thing to do. We're not going to do that. What we can do is remember our trig identities. Cosine squared plus sine squared, that just equals 1. So we have 1 over cosine squared of x, which 1 over cosine is secant, so this is secant squared of x. So the derivative of tangent is secant squared. We can find the other ones just like it. Cotangent is found basically identically. Secant and cosecant are 1 over cosine, 1 over sine. So you could find them using quotient rule. You could actually find them just using chain rule. 1 over cosines, cosine to the negative 1. And then you can use chain rule with that. And you will be doing those, by the way. But the derivatives of the trig functions are this. We already know that sine equals cosine, cosine equals negative sine. Tangent equals secant squared, we just saw that. Cotangent will be negative cosecant squared. The cosecant should kind of make sense there. Secant ends up being secant tangent, and cosecant ends up being negative cosecant cotangent. Couple things to look at. Aside from the top two, the derivative of cos get you other cos, and the derivative of things that aren't cos gives you things that aren't cos. All of the derivatives of the cos are negative. So if you can't remember if it's positive or negative, are you doing the derivative of co something? Then it's negative. And so we can use these, say we want the derivative of secant of x squared. The derivative of secant of x squared, secant x will be secant x tangent x. So here we have secant of something, so we'll get secant of something, x squared, tangent of the something, x squared, and then chain rule times the derivative of the x squared, which is 2x. So the derivative of secant of x squared is going to be 2x times secant x squared tangent x squared. And so we can use these trig functions the same way we'd use anything else. They can be in our product rules and quotient rules. They can and be included in chain rules. They can do anything that we've done. These are just some more rules that we have that we can use for derivations without having to go back to the definition. So today we saw product rule and quotient rule, plus the other trig functions, which you can now find. So that's what we're working on. Next time we'll look at some exponential and logarithmic functions. But until then, keep working problems, keep asking questions, and as always, happy mathing.